All right, let's go ahead and get started. I do want to welcome you back to Unit 7. This is chemical reactions. And in our last screencast, we were looking at factors that increase the rate of a reaction. And one way was the use of catalysts. And I mentioned that catalysts lowered the energy of activation. I want to get back to that now and talk a little bit more about how they do that precisely. So we said that they lower the energy of activation. That's the energy necessary to make a reaction proceed in the forward direction, and thus make reactions go faster. I want you to look at this diagram here, and you're going to see, for example, the potential energy as I move from left to right, the potential energy of going from the reactants, that's right here. This is the potential energy of the reactants here. And down here, the potential is the potential energy of the products, right? And this is time. And so on the x-axis, we have time. So as the reaction proceeds, you can see that the reactant potential energy goes down. We call this an exothermic reaction. There's a release of energy in this process. But the point is this, that for the red line, we have this increase in potential energy. In order for this reaction to go in the forward direction, I'm going to have to supply that amount of energy. It's called the energy of activation, and we're going to abbreviate it just like that with an E sub A. So that E sub A is critical to this reaction. I must place that amount of energy into the reaction in order for the reaction to proceed in the forward direction. That's even though the potential energy of the products is going to be lower than the potential energy of the reactants, okay? But what if I introduce a catalyst? Well, what a catalyst is going to do is it's going to lower that energy of activation so that that energy barrier, that amount of energy that I have to input in order to make the reaction go, is not quite so high. So what we see here is for the red, a normal potential energy diagram for a chemical reaction. But what we see with the green is that the energy of activation, even though the potential energy of the products, the reactants, and the products remain the same, the energy of activation is significantly lowered, making this reaction go much faster. So that's how chemical reactions, that's how catalysts work. They work by lowering the energy of activation. So we're going to notice that catalysts do not actually enter into the reaction themselves. They simply lower the energy of activation. This means a greater number of reactant molecules will have sufficient kinetic energy to cause bonds to be broken and made so that reactants can become product. In other words, the reaction proceeds faster than it would have if there had not been a catalyst present. So that's the action of a catalyst, all right? Okay, so I hope that is clear. All right. The important point for pre-AP students, and that is this. We're going to be covering two topics, oxidation reduction and nuclear reactions, but these are going to be tested separately. So we're not going to test these. I'm not going to test these together with the ordinary chemical reactions unit. So just to keep in mind. Expect about 5 questions on the semester exam from these two topics. Equilibrium will not be reviewed or tested until later. So we'll talk about equilibrium later. So oxidation reduction reactions. Let's talk a little bit about what we mean by oxidation and reduction. All right, oxidation reduction reactions are sometimes called redox for short. Redox oxidation reduction reactions. They're essentially any type of reaction where electrons are transferred. So that includes a lot of the reactions that we've already talked about. So by the way, we've talked about 5 types of reactions, right? Now, I do need to tell you that redox reactions or oxidation reduction reactions, however you want to say it, is not an additional type. Some of the reaction types that we've already looked at, including single replacement, double replacement, synthesis, decomposition, and combustion, are included. Redox is included in those categories. So it's not a separate category. So that involves a lot of different reactions, all right? So oxidation numbers or states are used to keep track of what is being oxidized and what is being reduced. And we'll define those in just a minute. Let's begin by learning how to determine the oxidation number on an atom. That's where we're going to start. Here are the rules for assigning oxidation numbers. First, for an atom in its elemental form, including diatomic elements, the oxidation number is 0. So if you see in a chemical reaction, for example, magnesium or chlorine gas, remember chlorine is diatomic, it's one of the Brinkelhoff elements, the oxidation number is 0. All right? Now, for the alkaline metals, that's the first column, the alkaline earth metals, second column, and the halogens, that's the 17th column, the oxidation numbers usually mirror the charge. For example, sodium is +1, oxygen in the 16th column -2. Number 3, nonmetals usually have negative oxidation numbers. Nonmetals, those on the right hand of the zigzag line, usually have negative oxidation numbers, usually. Number 4, hydrogen can be either +1 or -1, depending on what it's associated with. And finally, the sum of the oxidation numbers is in a neutral molecule is 0. The sum of the oxidation numbers is 0. And the sum of the oxidation numbers on a polyatomic ion is the charge on the ion, right? So if I have, for example, OH minus, the total charge is -1. So for example, oxygen would be -2 plus hydrogen would be +1, -2 plus 1, -1. That's the same as the oxidation number for the entire polyatomic ion. All right? Now, I do want to point out that oxygen always has an oxidation number of -2. That never changes. That never changes. All right. So here we go. Determine the oxidation number on the underlying atoms in the following compounds. All right. I want to know what the oxidation number is on the nitrogen, the phosphorus, the iron in this case, and the nitrogen here. All right. So what we're going to need to do is we're going to need to determine what the oxidation number is on everything else, right? On everything else. And from that, we can determine what the oxidation number is for a particular atom. So let's take a look at these now over here. Explain practice questions. This one involves a polyatomic ion. What is the charge in the chromium in the polyatomic ion Cr2O7 -2? Well, the oxidation number overall is -2. Remember that the rule was that on a polyatomic ion, that the charge would be the same as the charge on the overall charge would be the same as the charge for the polyatomic ion. Well, that charge is -2, right? And since oxygen has an oxidation number of -2, the oxygen has a total charge of 7 times -2, right? 7 times -2 is -14. So just for the 7, it's -14. Therefore, the chromium must be +6. Watch the reasoning here. It must be +6 since there are 2 of them, right? So if you have 2 times 6, that's 12. -14 is -2, right? The overall charge is -2. All right. Does that make sense? All right. Let's take a look at some oxidation reduction reactions now. Oxidation reduction reactions. So, these are known as redox again, and they are reactions in which electrons are being transferred. The electrons are being transferred from one species to another. Oxidation is the loss of electrons or the gaining of a positive charge. Okay? Oxidation is the loss of electrons or the gaining of a positive charge. Reduction is the gain of electrons, okay? Now, we're going to talk about how to remember that in just a moment, but I just want to give you a little preview. If you can remember this, oil rig, this little mnemonic will help you to remember what oxidation and reduction is. Oxidation is losing. Losing what? Electrons. Reduction is gaining. Gaining what? Electrons. So if you lose electrons, it becomes more positive. If you gain electrons, it becomes more negative. All right? All right. Let's move on. Use the mnemonic oil rig. So that's what we just mentioned. Oil rig to remember this. Oxidation is losing electrons while reduction is gaining electrons. So let's take a look at this reaction. We have magnesium plus oxygen. Remember, it's diatomic. Remember your Brinkelhoff mnemonic. So oxygen is diatomic, yields magnesium oxide. It's balanced 2 to 1 to 2. Let's determine the oxidation numbers for all of the elements here. Magnesium. Magnesium has an oxidation number of 0 because the rule is if it's by itself, it's 0. Even diatomic elements have an oxidation number of 0, right? So now let's do this. Let's determine the oxidation number of magnesium and oxygen in the magnesium oxide. Well, oxygen is always -2. Doesn't change. Magnesium is in the second column. It's +2. So what happened? magnesium went from 0 to +2. Is that oxidation or is that reduction? We went from 0 to something more positive. Oxygen went from 0 to -2. Is that oxidation or reduction? Another way to look at it is if the oxidation number goes down, that's reduction, and that's what happened here. So to go from here to here, from oxygen to magnesium oxide, that was reduction, right? So from here to there, that was reduction, and I'll put an R just like that. So going up 0 to +2, that must have been oxidation. So for every oxidation, there has to be a reduction. So in the above reaction, what's being oxidized and what's being reduced? So let's take a look at the answer. It says on the left side of the equation, magnesium is in the elemental form and has an oxidation number of 0. On the right side, its oxidation number is +2. In other words, magnesium lost 2 electrons. It went from 0 to +2. It lost 2 electrons. Lost 2 electrons in the process. And its oxidation number also increased. It went from 0 to +2. From oil rig, oxidation means losing. Right? Oxidation means losing. So magnesium is being oxidized. The magnesium is being oxidized. In contrast, oxygen must have gained 2 electrons since it went from an oxidation number of 0 to an oxidation number of -2. The oxygen is being reduced. All right? So the oxygen is going from 0 to -2. Oxygen is being reduced. All right, let me introduce a couple of different definitions here, and that is right here. The element being oxidized, magnesium in this case, lift this up so you can see it just a little bit better. The element being oxidized, magnesium in this case, is known as the reducing agent. So the thing that's being oxidized is the reducing agent. All right, it's reducing something else. The element being reduced, oxygen in this example, is the oxidizing agent. All right. So one more time, the thing that's being oxidized is the reducing agent, and the thing that's being reduced is the oxidizing agent. All right? So in oxidation, the oxidation number for an element increases. We've said that. For reduction, the oxidation number decreases. All right, so let's move on. We want to talk about oxidation and reduction half reactions now. So we said for every oxidation, there had to be a reduction and so forth. Oxidation and reduction are always coupled, since electrons which are lost by something must be gained by something else, right? Electrons don't appear and disappear. A half reaction is that part of the redox reaction which pertains to whether electrons are lost or gained. So, and here's a quick note. For oxidation half reductions, the electron or electrons are on the right-hand side. So remember, oxidation is on the right-hand side. The electrons are seen on the right-hand side. Reduction, they're on the left-hand side. So let's take a look at this half reaction right here. We have iron +2 becoming iron +3 plus an electron. Well, the electron is being lost, right? Oxidation is losing. You're going to see that electron on the right-hand side if it's an oxidation. So oxidations, you'll see the electrons if it's a half reaction on the right-hand side. For a half reaction involving reduction, you're going to gain an electron. Here it is. You'll see that electron on the right-hand side. So one more time. If you have a half reaction that is an oxidation half reaction, the electron will be on the right. But if it's a reduction half reaction, the electron will be on the left. All right? The electron will be on the left. All right. Notice that in the oxidation half reaction shown above, iron is losing an electron. Oxidation is losing. Right? Oxidation is losing. Now, and the second half reaction is an example of a reduction. Since hydrogen is gaining electrons, you can also tell it's a reduction because the electron for this half reaction is on the left-hand side. Folks, I think this is a good place to end this one. I'll meet up with you on the next one. I'll see you then. Thanks. Bye-bye.